All right, so this section we're going to focus down on Ethernet and the IP protocol. So there's a couple things. We're going to talk about how Ethernet supports the network communication, IPv4 in that communication, IP addressing, etc. So starting with the basics of Ethernet, and there was a lot of different communication protocols before Ethernet was finally ratified. So Ethernet was the one that won out, so to speak. There was a lot of other ones, Token Ring and some other ones way back in the day. But unlike wireless, Ethernet uses a wire communication. It's typically over twisted pair, but it can also be over fiber optics and even coaxial cables using different frequencies. Ethernet operates at the data link layer. So if you guys are familiar with the OSI model, we're working with this physical as well as the data link layer. And this family of networking technologies is usually referred to as the 802.2 and 802.3 standards. 802.3 standard is typically your physical network, so Ethernet. Your Ethernet is going to support bandwidths from anywhere from 10 meg all the way up to 100 gig. And I've seen everything in between there. So you have 10 meg, 100 meg, 1,000. Then you have 2.5. You're going to have, 2.5 generally. Then it jumps up to 10 gig, and then from 10 gig you can have 40 gig, and then on upwards to 100 gig. And there's some variants in between there. They're not as common these days. They were just incremental levels, but most of the common ones you guys are going to see today are 1 gig and 10 gig interfaces. Every now and then you'll still get into some 10, 100 stuff, which in today's world is going to be pretty rough to use. All right, so Ethernet frame headers, you guys should be familiar with this. You guys will get quizzed over this section, I'm sure. So you'll have your preamble that will come in here. Again, this is going to get covered in more detail inside the curriculum. This is your first 8 bytes, and then you have this section here, which is your 64-byte section. Anything less than this is going to be considered a fragment, and therefore it's going to be discarded by most sessions. Now again, frames with more than 1,500 bytes are considered jumbo frames or baby giant frames. Typically jumbo frames is the terminology that's used. And this is what I was talking about in the last section, where you can adjust those sizes and transfer more data. But you have to make sure everything on the network speaks that. If not everything on the network speaks that, then those packets are going to get lost. So a Ethernet frame size is going to be a max of 64 bytes and a minimum of 64 bytes, a maximum of 1518 for your standard Ethernet. And then that takes you through here where you have your destination MAC address, your source MAC address, what type of packet it's going through or the length, and then the data that's encapsulated inside here, and then your frames check sequence, which is just going to be a field to help make sure you get these in the right order. All right, so with your preamble and your start frame delimiter, these are just different fields and their explanation as to what's going on. This is used to synchronize between the sending and receiving devices. The destination MAC address, you guys should be all familiar with MAC addresses on your devices. Everybody should have a unique MAC address. Even in the virtual world, you're going to have a virtual MAC address. Source MAC address, this is going to be where you are originating from and sending it out to. And then you can see the different particularly this frame check sequence, use this terminology here of CRC, or your cyclic redundancy check. On your Ethernet MAC address, you're going to have a 48 binary value that's expressed as 12 hexadecimal digits. So for example, you may see it with dashes over here, you may see it with colons, and you may see it with periods. Note that your periods are going to group them together with the 4 octets here instead of there. So you want to be familiar with this and be able to translate between each one of these 3. Depending on what you're doing, you may need to use a different format structure. All referring to the same address, it's just how they're being represented. All right, so IPv4, this is going to be where you get most of your services today and allows end devices to exchange data. IPv4 and IPv6 are the main network layer protocols. You could use things like OSPF and your Internet Message Protocol, ICMP, or other network layer protocols. This one's going to be more for routing, where your ICMP one here is going to be more for pinging and testing and confirmation of message delivery. Let's see, your end addressing is going to be configured with a unique address between each one of those. Encapsulation, again, that refers back to the PDU going across the transport layer into a packet. And routing is going to be based on best path as well as the direct packets towards the destination host. Performing, let's see, de-encapsulation performed by the destination host is going to be when they tear this packet back down. On this network layer, this is just again going to be an animation that shows you how to go through here. You'll see this inside the curriculum. IP encapsulation, again, this is your transport layer where you're getting your segment header and your data going down into this data layer on the network layer encapsulation with an IPv header in front of it. Connection list, this is going to be your UDP that we talked about before. This is all best effort, and IP is inherently unreliable for packet delivery as it's not necessarily guaranteed. An operation in independent medium, for example, copper, fiber optic, wireless, it's all going to depend on how that's transmitted across there. So connection list analogy, this is going to be, we send a letter out, you send it to a mailbox, it eventually gets there, but there's no way to confirm that it's ever getting there on a regular piece of mail. Where when we send a packet over a connectionless network, it's very similar. So we're going to send an IPv header and then a segment, and it has to traffic its way through the network. If you've got some bad routing or something in here, it could just sit here and circle and go around forever. So with best effort, it's an unreliable network layer protocol. IP protocol does not guarantee that all those packets are going to be sent, that they'll end up being received. Other protocols manage the process of tracking those packets, such as TCP, and configure the best reliable effort to get that packet across here. Media independent, this is basically referring to the different medias that you may see. So a lot of times today, most of what you're going to see is copper Ethernet going across here. You may also see your wireless devices going across here. On the higher end side, you may see your optical fibers that go across here now. This is getting more and more popular, generally not clear out to the desktop, but at least at the devices connecting between your routers or your routers and your switches, etc. And your copper serials, this is also disappearing. This is kind of an older transmission, T1s, T3s, that kind of thing. You may have had that kind of serial connections going across there. All right, so in the IPv4 packet fields, again, this is what an IPv4 packet looks like. You're going to have your version up here. You're going to have the internet header length, and then it's going to work its way with these different options. This section here is what's called diff or diff services. This is where you're setting whether you want these packets to have a higher priority than another packet, and then the actual length of the packet itself, the identification, the flag, and the frame offset, time to live, protocol, header sum, and then your IP address information. Following down here is your data. Now, this all seems like a lot of information to memorize, and eventually as you start working through networks, you just need to understand the basics of how it works, because there's things that we can do to manipulate this, and that's what you're going to be looking for as a cybersecurity analyst, is anomalies here. So for example, if I set flags that shouldn't typically be set, that's what you need to be able to identify that something weird is going on there. Or if source address information and my destination information inside of a packet is being manipulated or changing when I'm looking at it with Wireshark, then we know that somebody's attacking you inside the middle. All right, so IP addressing basics. This is going to be your IPv4 32-bit address. It starts with your network portion and then the host portion. So depending on what your subnet mask is, will dictate which portion is the network portion as well as which one's the host. And so in the standard 192.168 private IP address space, the 192.168.10 is going to be the network portion, and then your host is the last octet that's out here. Your subnet mask is going to help you identify what network host portion you're on. Your default IPv4 address is required to reach all the remote networks and the DNS servers, required to translate those IP addresses to domain names or vice versa. And then your subnet mask is going to explain this with ones and zeros. So your internetworking class is really going to dive into subnetting and understand what subnetting is. With that subnet mask, you can AND all this together and you get ones and zeros, etc. Again, they're going to cover that in more detail in that class. In the prefix length, this is written as a slash notation. So instead of having a subnet mask of 255.255.255.0, it's commonly written as a /24. And you will typically hear these referred to as /24s, and being able to convert from a /24 to an IP address over here for your subnet mask. You guys will memorize that. You guys will figure that out. In the real world, you'll more likely use an IP addressing calculator. Even the guys that I went to college with, I asked them all today, hey, do you still remember this subnet? Once you get the basic subnets, people remember, but after that, they just use an IP address calculator. So these are your typical slashes that you should be familiar with. You have a /8, which is this first octet field, /16, this one here, and then 24. These are all chopped into much finer networks here, so /25 through /30. Note that on things like a /30, there's only 2 usable IP addresses inside of there. So this typically isn't used in like home networks. You almost always have a /24 at minimum, which means you have 254 IP addresses available on the network, usually more than enough for a home network. If you end up needing more, then you just kind of back it up to a bigger IP address space. These /30s are typically used for links between routers where you want to route network traffic, or maybe on your IPv tunnels, things like that is typically where you use /30s. This is talking about the logical ANDing, and this is so you can get the final IP address that gets ANDed together. You're basically adding bits. So if it's a 1 and a 1, it gets a 1. If it's a 1 and a 0, it gets a 0, etc. Understanding how that works, so like we said here, you have your network address that's been converted over to ones and zeros. If we have a 1 and a 1, then this equals a 1 down here for my address. If I have a 1, 1, 1, it's 1, 0, 1, 0. So the only time you get ones down here is if there's a 1 here and a 1 in this field, and then you get a 1 down here. So again, this is going to be your network address, which is the 192.168.10.0 network. And again, the videos that they have are fantastic for describing that in further detail. With subnets, you're going to have broadcast domains. That's the reason that we subnet. And the idea is to get that broadcast traffic to not be so big. So you don't want to just go to your house and throw up a /16 and call it a day, or create a network and just do a /16. Because if you have 400 users on that network and they all send out broadcast traffic, it's going to slow your network down because they are constantly broadcasting to everybody. What you want to do is kind of limit your broadcast domain. Now, this doesn't necessarily mean that you want to limit it way down. In other words, you don't want to throw up a /30 for every single connection. That doesn't make sense. But you may want to be able to knock that down to at least a /24 in order to limit the broadcast domains between different networks. That way, if you want to send traffic across there, you just have to have a route going in and you can limit that traffic. Broadcast domains, again, typically you'll see this broke up into groups or services, particularly at a larger domain configuration. So for example, administration is going to live on the .1 network, human resources on .3, students on .2, and accounting on .4. And again, the reason they do this is, one, to limit the broadcast domain. Students are going to talk to other machines, accounting's over here. But in order to get to this traffic, you have to end up routing through this over here. And like this particular one, you're going to see this router has 4 Ethernet interfaces, and therefore that connects up to the switch, which then connects out to all your clients. All right, so types of IP addressing. This is going to be where your Class A, B, and C come into play. Class A is typically for extremely large networks that have more than 16 million host addresses available. Not commonly used in most networks because that's way too big of a broadcast domain. Your Class Bs are a little more common. You're going to see things like /16s. Notice that this IP address space starts with 128, goes all the way to 191.255. This is going to give you about 65,000 host addresses. And then typically what you see in your house or maybe just smaller networks is going to be your /24s, and this all lives in the 192 ... space. So the most common private network is going to be 192.168.1 or .10 or something like that, but 192.168, you can almost immediately know that that's going to be a private address space. If you are working other private address spaces that they kind of refer to here, these are all the classes, but they haven't talked about the private ones yet. So that's the next slide. So again, Class A is going to use up 50% of all the space that's available out there, and then we finally chop that up into other spaces. Okay, so here's your private address space. This is going to be your 10 network on a /8 is commonly used. When you're using a /12 or something like that, they're going to use 172.16 or 172.16.00 all the way up to 172.31. So you can use any of that in between there and use a bunch of /12, or this is a /12. A lot of times you'll use /16s to chop this up a little bit. And then the private address spacing of the 192.168 is typically used to slash it up into 24s. So you should memorize these blocks, and that will allow you to know what your private address space is. This is probably a good quiz question. Key thing with the private address spacing is they're not allowed on the internet. So you must have something that is routing those, and because they're typically filtered by your firewalls and such. So I can't just go with a 192.168 address and jump on the internet. I have to have some kind of public IP address, and that's where a lot of times in your home network, this gets NAT translated. So this means that we are network addressing from this private IP address space over to a public IP address space. And you can see those different networks and how that may be sent out here at the ISP levels. All right, so your default gateway, this is going to be where you set your forwarding decision. In other words, where on my network is going to translate all these IP addresses for me. And so on your most home networks, it's usually the .1 or the .254, depending on what you have your router set up on. Out in the internet, in the real world, there again, it could be any IP address, but .1 and .254 are the most common ones that you'll see. Or in this case, 253 is also a common one. So your default gateway, this is where your network traffic can be routed to get to other networks. On a network, a default gateway is usually a router that has a local IP address in the same range as your hosts. It can accept data from that local network and forward it out of the local network to your internet route, and then traffics that out to other networks. A default gateway is required in order to send traffic outside of that local network, so outside of that IP address space, and traffic cannot be forwarded outside the local network if there's no default gateway. So you got to have a default gateway configured in order to do that. So your host routes going to a default gateway, these are all sent based on DHCP, and so that's usually sent automatically through DHCP, or you can configure this manually. On IPv6, they actually advertise the default gateway out to everything, or you can again configure it manually there. Having a default gateway configured creates a default route within the routing table of the PC, and then a default route is a route that allows you to send that out. So you can set that manually on a PC, again, with your IP address space, but I can also dictate my routes going out on a PC as well. So on a host routing table, for example, if I use route print, this is common on a Windows, or netstat-r, this is going to display the routing table going out there. So if I was to pull up a command line and do a route print over here on this screen, you guys can see the routes that go out on my particular network. My default gateway is 192.168.1.1, which is common with most home networks. This is going out my local IP address of 192.168.1.99 and has a metric of 25, which means this is going to be a higher priority network. You can see in order to get to these other networks, I have routes on my PC. That's because I have local IP addressing on these particular ones. So if we look at all the adapter lists on this particular machine, you can see that I have a Palo Alto network adapter. These are all your MAC addresses that we referred to earlier. You're going to have, I've got an Intel Ethernet link, and then my laptop dock also has its own Ethernet link. My Encap, this is typically going to be used for your Wiresharking. Allows you to have a loopback adapter that you can send traffic to. My wireless adapter, I have a couple Wi-Fi virtual adapters. This is going to be for my Hyper-V that connects down here. I also have a wireless LAN, so like cell towers, I have a wireless adapter there, Bluetooth, and you're going to have the different routes that allow you to get outside of that. So, and then IPv6, you're going to see a different route table. So you can see that I have a default /1 on a /28. That's my default metric going out here. All right. So they're going to explain this just similar to the way I did there, but the idea is that you can test these routes. So if you're trying to send traffic out to something and it doesn't match one of these here on a host routing table, it's going to send it out this default network. And therefore it's going to hit this gateway, and that gateway is going to have to look up in its routing table to figure out where to send that traffic. All right, so IPv6, we talked a little bit about this before. The reason it was designed was to be a successor to IPv4, as they assumed that we were going to start running out of IP addressing space. And we have for the most part. However, there's been a resurgence within IPv4. So for example, Aaron, who is a very large IPv4 holder in the typical North America area, they ran out of IP addressing, for example, in July of 2015, reclaiming some of those back now. You also have the LACNIC, RIPE over here, AFRINIC, and APNIC over here in the far east. IPv6 has a larger 128-bit address space, and so you have a lot of possible IP addresses, 340 undecillion. Mobile providers are leading the way with using IPv6, and that's because everything has a public IP on the IPv6 side. Most ISPs and content providers such as YouTube, Facebook, Netflix all have converted over to IPv6. Even Forte State has an IPv6 address space available and website available on IPv6. And many companies like Microsoft, Facebook, and LinkedIn are still transitioning to IPv6 only internally. The depletion of IP4 address space when moving factor for going to IPv6. So Internet of Things is what I was talking about in the last section. That is really what sparked this up, is we have lots and lots of devices coming up with IPv6. Those computers, tablets, and smartphones, everything in between needs to have an address, and you are running out of spacing. Again, NAT was going to be the biggest thing that helped with that. And it has come to help begin that translation of that. Now, they're saying that there's still issues here. Again, me personally, there's IPv6 out there, people have converted, but IPv4 is still very strong. It's just being natted in order to make that address space work. All right, so IPv6 is a little bit different in that you have 128 bits in length and is usually written as a string of hexadecimal values as opposed to your standard decimal that you'll see with IPv4. Every 4 bits is represented as a hexadecimal digit for a total of 32 hexadecimal values. An IPv6 address is not case sensitive, and therefore it can be written with either uppercase or lowercase letters. Again, the letters section of this is part of your hexadecimal, so A through F. So normally when you're writing IPv6, it's going to be in this format that you see here. So X, X, XX, all the way through there. Each X is a single hextet which has 16 bits. So these are all examples of IPv6 addressing in their preferred format. However, you may see other formats. For example, if you noticed on my my route table that we didn't see these really long ones all the way through there. So if I go, let's see, CMD, and I do ipconfig, and we take a look at some of these IP addresses on my local machine, you'll notice that this is an IPv6 address, and we can see how that works in between there. You can see these IPv6 addresses, but no, I'm missing something here, right? I get 2 colons together. I'm missing the 4 that's in between there. And what they're going to do is tell you that anything that you have zeros in between there, you end up omitting those as long as they're leading zeros. So for example, here I would omit this 0 and I would just put that as DB8. I have 4 zeros here, so I may just have a 0 here. A lot of times this will be even closed down further where you just see the 2 colons together. And you can see that here in this notation here. So the double colon just indicates that there was a bunch of zeros in between there. So for example, at the end of this one, to compress that space, you'll notice that they do a colon. These are all zeros clear up to this 2, and therefore you're going to see 200 here, omitting the 0 in front of that. Makes for to be a little more complicated, to be honest. All right, so for example, IPv4 in the address space that you see here, 192.168.1.10 is the dotted decimal with a subnet mask of 255.255.0 is usually indicated like this, 192.168.1.10/24. This /24 is called a prefix, where in IPv6 it's referred to as the prefix length. Similar to IPv4, that length is represented with a slash notation and is used to indicate a network portion, which can range anywhere from 0 to 128. It's strongly recommended to use a 64-bit address on most networks. That's Cisco pushing a little harder on IPv6. All right. So in summary of Ethernet and IPv protocols, we're going to see Ethernet and wireless networks are the 2 most popular LAN technologies that survived. It operates at the physical and the data link layer and uses the standards of 802.2 as well as 802.3. Remember, 802.3 is going to be more your physical connections. So whether you're using Ethernet or wireless LAN, etc., like wireless is 802.11 standard. The MAC address can be represented using either colons, dashes, or periods in between. Remember that when you're using periods, it puts 4 of those together, where these are usually 2. IPv4 and IPv6 are the principal network layer protocols. IPv4 is 32-bit, IPv6 is 128-bit. Memorize those numbers as well. Your prefix length is the number of bits set in the subnet mask, and therefore it's written as a slash notation using a / by the number of bits that are set. To get your network portion of this and your host portion together is called ANDing. Be familiar with what ANDing is. Class A, B, and C are all different ranges of IP addresses. Know those ranges a little bit. You should pretty much have those memorized. The router is connected to what is called a default gateway for a local network segment. On a Windows host, you can use route print or netstat-r, either one of those, in order to get your output. So again, if I do this one, which is route print, this is what I would see on my local network for a route print statement. You see route print, and then all the network here should be a very similar output of doing netstat-r, which will also print out that route table. Whoops, I forgot to spell that correctly. Netstat-r, and you'll get that routing table out there as well. Either one of those commands will do the same thing. 2 rules to help reduce the number of digits is you can use decimal notation or a double colon in order to reduce the number of digits that are needed to represent an IPv6, and a prefix length can be anywhere from 0 to 128. And that covers this recording.